Okay, so let's start to review a little bit what we talked about last time. Last time we talked about the Lewis structure, right? Lewis structure, and we talk about the Lewis structure for elements, for the ionic compound and molecular compounds. For the elements, then you just need to count how many valence electrons that for these elements. Then you assign single dots on each side until the four sides are 4, then we can add a little bit more. Like nitrogen, right? Nitrogen has a 5 valence electrons. So you're gonna have 2 electron, the valence electron paired together. So that is the nitrogen, and this is aluminum. Okay. For the ionic compound, again, ionic compound is made by cations and anions. So when you write the Lewis structure, you need to write the charge the particles, the cations and anions. So that's why if you write the sodium chloride, then you're going to write the sodium ion and the chloride ion. And then this is the Lewis structure for the sodium chlorides, right? This is a Lewis structure for sodium chlorides. And if you have another one like aluminum chloride, again, you're gonna have aluminum in the middle and the chloride on the side, and write the 3 chloride ion over there. Then that's it. Well, this one is very similar like the molecular compound, but you need to make sure that one has the charge, right? They have a charge. So this is the only difference between molecular compounds and ionic compounds. One has a charge, one don't have a charge, right? So this is aluminum chloride for the Lewis structure. And also when we write the molecular compounds, for example, like a CO, carbon monoxide, well, then we need to count how many valence electrons for this compound. And then we set which one. Okay, so let's just keep going. There's a 4 for carbon, oxygen, that's 6. Totally, we have a 10 valence electron for this guy. So we're gonna have a carbon and oxygen up there. When you're assigned the Lewis dot, first, we write the dots between the 2 elements, which is the shared electrons. First, then that means we're collected together. And once again, when we do the shared electron, we usually just do 1 pair, which is a single bond. And then we try to assign one of this, at least one element's octet. Okay, so this is what we do. Now we have a 10, so 2, 4, 6, 8, and 2 more. So this is a 10 dots, which means you can only assign 10 dots of there, but obviously only carbon follow the octet, but the oxygen only 4. So this is not a correct Lewis structure for the carbon monoxide. So definitely we need to change this, right? We talk about if we short off the dots when we assign the Lewis dots, that means we need to think about whether we're adding 2 double bonds or triple bonds. So what you're gonna do, you're going to just put the lone pairs into the shared area. So now you have, the people may ask, okay, why can't I share the oxygen, the lone pairs up there? Well, you can think about it. We need to add it. We need to add the dots to the oxygen. If you're those 2 pair, this 1 pair is already belong to oxygen. Doesn't matter you're putting to the share area, it's already belong to the oxygen. Even you put this into there, it's still not increasing the total amount of the oxygen, right? So those lone pairs must coming from the carbon instead of oxygen. You understand what I'm talking about? Okay. Yeah, so now you're going to move this to the area. So let's see. it will become something like that. Now, carbon, you see, carbon still no change, still have 8. You see, still have 8. But right now, oxygen, they become from 4 dots to the 6 dots, right? But still not enough, which means you're still going to move another pair of the electrons to the shared area. Then it becomes something like that. Right? So now you see the carbon still 8 dots, and the oxygen now it also going to have 8 dots. So that's why this is correct. And you replace those 3 paired electron, it become a triple bonds. Become a triple bonds. Then that's it. That's it. Does it make sense, right? So that's going to be the Lewis structure for carbon monoxide. Well, if you're saying, can I doing something like that? Well, I'm putting the dots over there. Sure, that's exactly the same. Okay, those are exactly the same. So it really doesn't matter which one is correct. Are you clear? Okay. So this is the Lewis structure for the molecular compounds that we're talking about. Okay. And also, last time we also talk about some of the exception, and there's one thing we talk about is how can we determine? We talk about there's the carbon monoxide. This is carbon monoxide. Sorry, carbon dioxide. This is carbon dioxide, and actually we have another structure like this. This is also the Lewis structure. Well, this structure also follow the Lewis structure. And if you're talking about every elements over here are all 8 electrons around, 8 valence electron around, right? Single bonds containing 2, triple bonds containing 6. So each of those elements all have 8 electrons. So both are follow the octet. But the point is, which one is the correct formula? Which one is the correct structure? Why? So this is what we discussed. We haven't. Well, I talk about this one is correct, but I didn't talk about why. So here today we're going to talk about why this structure on the left side is correct. Okay. So the following part we're going to talk about the one concept. It's called the formal charge. You probably, anyone heard of the formal charge before? No? Yeah. So this is the college chemistry part. Okay. Formal charge is helping us to understand which structure is correct. And in general, the formal charge is try to find the charge for each of the elements inside of the molecule. Inside a molecule. So the rule here is the more zero, the better. The more zero, the better is for formal charge. Well, how to calculate the formal charge? So generally, the formal charge, the rule for formal charge is equal to the number of valence electron subtract 1/2 times the number of the electron in bond plus the number of electron not in bond. Number of electron in bond, number of the electron in bond. 1/2 times number of electron in bonds and number of electron not in bonds. Okay, so looks like this equation is complicated, but let's see, actually it's not that complicated. Let's just using the this carbon dioxide as an example. So if we want to figure out the formal charge for the oxygen on the left side, well, let's just based on this, how to calculate. First, oxygen, this is oxygen. So the number of valence electron for oxygen is 6. So you're gonna 6 subtract 1/2 of the number of electron not in bonds. So the oxygen connect with double bonds. How many valence electron in the double bonds? 4, right? So the oxygen will containing 4 electrons in bonds. So 1/2 times 4. And plus number of electron not in bonds. How many valence electron for this oxygen not in bonds? 4, right? We have 4 dots. So you're plus 4 over here. So that's why this formal charge calculation is 6 minus 1/2 times 4 plus 4. Okay, then you see 6 minus 2 plus 4. Then you got 6 minus 6. Then you got a 0. So the formal charge for this oxygen is a 0 charge. Okay, this oxygen is 0 charge. Then if we see this oxygen, well, generally it's the same thing, right? Those two are exactly the same. They also has 4 dots not in bonds and 4 dots in bond. That makes sense, right? So the formal charge for this one is 6 minus 1/2 times the number of electron in bonds, which is 4, plus number of electron not in bond, which is also 4. So 6 minus 2 plus 4, then that's 0. So this oxygen also the formal charge, which is the perfect for oxygen. Okay, yeah, we talk about you need to have as much 0 as possible for the formal charge. Okay, and then if you see the carbon over here, valence electron for carbon is 4, right? And subtract the number of the 1/2 times number of electron not in bonds. Carbon containing all bonds, right? That's 2 double bonds. Each double bonds containing 4 electrons. So that's 8 electrons in bond. So 1/2 times 8 plus number of electron not in bond. Well, there's no dots for this carbon, so no electron not in bond. So you put a 0 over here. So 4 minus 1/2 times 8 plus 0. So 4 minus 4. And this is also 0, 0. In another word, after calculation, you see the oxygen, carbon over here, the formal charge are all 0. So that is why this structure is perfect. Okay, this structure is perfect. But if we look this one on the right side, this oxygen, so 6 minus 1/2 times number of electron not in bonds. This guy only have a single bond, so 2 electrons times 2, plus number of electron not in bonds. Well, 6 dots not in bond. So you see, this is one is a 6 minus 1/2 times 2 plus 6. That's a 1 plus 6. That's 7. 6 minus 7, you got a minus 1. So the oxidation. Not the oxidation, sorry. The formal charge for this oxygen is minus 1. Okay, the formal charge for this oxygen is minus 1. And then if you're looking at this one, this is a 6 minus 1/2 times the number of electron in bonds. This guy has a triple bonds for oxygen. There's a 6 electrons, so you times 6. And plus electron not in bond, which is 2. Then you will see this one is a 6 minus 3 plus 2, that's 5. That's going to give you a positive 1. So this oxidation, this formal charge for this oxygen is plus 1. This one is negative 1, right? And for the carbon, it's still 0. Why? Because this carbon still containing 4 bonds, right? They containing 8 electrons in bonds, but they don't have electrons. So this is a 4 minus 1/2 times 4 times 8 plus 0. So this is still 0 over here. So you will see, okay, for this structure, they have a one oxygen -1, one oxygen is +1. And so this is not stable. Okay, so that's why we talk about naturally the structure or the molecule usually they prefer to be symmetric. Okay, prefer to be symmetric because that way is the easiest way or the natural way to make the structure stable. Okay, yeah. I'm not saying, I mean, you cannot have this kind of structure suddenly. Maybe during some of reactions, you may have this compound, I mean, suddenly generated this kind of structure, but definitely it's not stable. So they eventually will convert to the structure like this. Are you clear? Okay, so formal charge is helping us to figure out which structure is correct, which structure is not stable. Another example is just the BF3, which is a boron trifluoride. So last time we talked about boron trifluoride actually is an exception because a boron only have 3 bonds, which is 6 valence electrons and no dots over here. So the structure will be like this. But this one is an exception, which is not follow the octet rule for the boron. But if you follow the octet rule, generally you can also write the structure like this. If you write the structure like this, actually is follow the octet. But why this one follow the octet, but it's still not a correct structure? But the one that follow the octet, not follow octet is correct. So that's why we're still going to using the formal charge to determine it. If you're looking at the fluorine over here, you can calculate. Fluorine has a 7 valence electron and subtract number of electron in bonds, which is 1/2 times 1 times 2. 2 electrons in the single bonds, plus how many dots over here? 6. So this is 7 minus 1 plus 6. This is 0. Other fluorine is exactly the same, so all 0. And if you're looking at the boron over here, boron only have 3 valence electrons. And then that's 1/2 times number of electron in bonds. They are having 3 single bonds, which is 6 dots. Then you times 6. There's no dots shows over here, which is 0. And then 3 minus 3, you got a 0. So this formal charge for each of the particles over here is 0, are zeros. But if you're looking at here, this fluorine has a 0 charge, formal charge. This fluorine also has a 0 formal charge. But if you're looking at this fluorine, it's different. This one is 7 minus 1/2 times number of electron in bonds. Double bonds has a 4 electrons, so times 4, plus number of electron not in bonds. We have 4 dots, so plus 4. 7 minus 1/2 times 4, that's 2, plus 4, that's 6. 7 minus 6, you got plus 1. So this guy has a plus 1 as a formal charge. And if you're looking at the boron, it has 3 minus 1/2 number of electrons in bonds, which is 8 over here. You times 8. Number of electrons not in bonds, there's no. So 3 minus 4, you got a -1. So this guy has a -1, fluorine has a positive 1, and the other has a 0. So that's why this structure is not stable. This structure is not stable. Are you with me? Okay, yeah. And by the way, if you're looking at this, I didn't talk about more in detail, but you see that formal charge for the molecule, since the molecule is a 0 charge, right? So if you calculate the sum of the formal charge for each of the elements together, should also be 0. That makes sense, right? I mean, you cannot see you find the whole elements is 0 charge, but you got if you add the formal charge all together, it's not 0. That does make sense, right? So each of the formal charge of the elements, you add them together should be 0, right? For example, this is 0, 0, 0, 0, 3 elements are all 0. But here, this is 0, 0 for the 2 fluorine, and the boron is -1. This fluorine is a positive 1. Okay, so -1, +1 make it 0. Okay, so it doesn't matter how you calculate the formal charge for the elements for the compound, the sum should be 0. Otherwise, it doesn't make sense. So this is how we calculate the formal charge. Please get out your study guides, the last page of your study guide. The question number 6 is to give you the one of the examples. So it's the formal charge. The last page. The first question of the last page is okay. We have the Lewis structure of there. Determine which structure will be the best structure for the compound. Okay, so let's review this one. Okay, the answer is this one is correct. Okay, the one on the right side is correct. If you're looking at the formal charge, then we can just then we can find the answer. Oxygen over here, if this guy has a single bonds, then you have a 6 minus 1/2 times 2, because 2 electrons in the single bonds plus 6 dots. So 6 minus 1 plus 6, that's 7, is a -1. So this guy has a -1 formal charge. For the oxygen, this one, that's a 0, because they have a 6 minus 1/2 times 4 electrons in the bonds plus 4 dots. So you got 0. Hydrogen here is also 0, because that's a 1 minus 1/2 times 2 electron, because hydrogen only combined with one double bonds or one single bonds. So times 2 plus 0, then this is 0. Nitrogen over here, you see this is a 5 minus 1/2 times 8. There's a 8 electrons in 2 single bonds, 1 double bonds, so that's 8, and no charge, no electron in the outside, so that's 5 minus 4, that's a +1. So you see, this is -1, this is +1, the other are the zeros. So this is a structure like this. And which one? This oxygen is 0, because this structure is exactly on the like this, right? So this is 0. Hydrogen also 0, because they only combine with one single bond. And the oxygen over here is also 0, because that's 6 minus, you see, 1/2 times number of electrons in the bonds, that's 4, and the plus 4 electrons not in bonds, so that's 0. Nitrogen here have a 5 subtract 1/2 of the electron in the bonds, which is 6, and plus the bond not in bonds, which is 2. So 5 minus 3 plus 2, that's 0. All right, so that's why this structure has every formal charge for each of the particles are 0. So that's why this structure is the most stable one. Okay, so now based on the structure, and we can make a summary, because you see we don't have too many of the non-metal compounds, so it's pretty easy to make a summary for this. For example, for carbon, you see carbon only have a 4 valence electron. To make the carbon as a 0 charge for formal charge, the best way is just making a 4 single bonds, right? 4 single bonds is 4 subtract 1/2 times 8 electron plus 0, and this is the best way. Then you can have this formal charge. That makes sense, right? Which means you're gonna have a 8 of the valence electrons around the carbon. Then that's 8 of the valence electron in bonds. Then that's gonna be best. Or you see, either you have 4 single bonds, or you can making like 2 double bonds. This is also correct, right? This is also stable for carbon. Or you can make a 1 single and 1 triple. This is also containing 8 valence electrons in the bonds. That makes sense, right? So, or you can have 1 single bonds, or 2 single bonds and 1 double. This is also. So that's why you see for carbon, you have a lot of the variation of the structures that they can make. So that's why organic compound, most of them made by the carbon, because you can have a lot of the shape, different options can make the structure. Okay. But if you're talking about nitrogen, nitrogen has a 5 valence electron. To make a 0, then the best way is just 1/2 times 6 plus 2. Then you can make a 0. In another word, you're going to have a 6 valence electron in bonds and just 2 dots on the outside, right? So for nitrogen, the best way to making probably like this. You have one pair lone pairs and 3 bonds, single bonds. Or you can making 1 single bonds, 1 double bonds, right? Or you can making 1 just triple bonds and lone pair. This is also the option for nitrogen, right? They give you 3 different options. Carbon has 4 different options. And that is why in the organic compounds, we also has a lot of the nitrogen in the organic compound. That makes sense, right? Then if you're talking about oxygen, oxygen has smaller options because oxygen has a 6 valence electron. Then to making the formal charge as a 0, then you're gonna have a 1/2, then you time 4 plus 4. Then this is the best options for oxygen. So either you can have 2 lone pairs and 2 single bonds. This is one of the option, or 2 lone pairs, 1 double bonds. This is the options. Okay, so oxygen only have those 2 options. If you're talking about oxygen has the triple bonds, this is possible, but very rare. Like what we talk about carbon monoxide. This one, you see, carbon monoxide is not stable. But this is the best options for carbon monoxide. You see, we talk about neither carbon and oxygen would like to have a triple bonds. This is not stable, but we still have a carbon monoxide. We'll just let you know carbon monoxide is not as stable as carbon dioxide. Okay, yeah. So this is options for nitrogen. And then if you're talking about those hydrogen, fluorine, iodine, and bromine. So those are only just need 1 electrons. The best way is just a single bonds, right? Because all of those only just need single bonds, then that's it. Either this hydrogen only just need 1 single bonds. Fluorine also need a single bonds. Chlorine also just need a single bonds. And iodine need a single bond. And the bromine, you see, 7A group, they only need just a pair 1 of the electrons. So they only just need 1 single bond. If you have a double bond for those guys, that's impossible. Okay, generally, definitely it's not stable. Are you with me? Okay, so now you see, we already talked about most of those are the very common elements for carbon, nitrogen, oxygen, hydrogen. So that's why if you're looking at the Lewis structure, in most of the cases, you will tell whether this structure is stable or not. Does it make sense? Right? Okay, so now this is what we talk about the formal charge. The next part we would like to, let's take a break, and then we will talk about geometry of the molecule. Geometry of the molecule. Okay, so the next part we would like to talk about the geometry of the molecule. And for the geometry of the molecule, and we're going to talk about one of the model. And this model is helping us to understand why we can have the different shape of the molecules. For example, everyone knows the water is not a straight structure. Water is a band structure like this. And you see the snowflake. You see the snowflake. And this is the real picture that you can see for the snowflake. Why the snowflake is like a hexagon shape, right? This is a hexagon shape, and they can cut. They all have the angles between each of those flake is 1 point. Why we have the structure like this, right? This is generally is because of the foundation, which is the molecule shape of the structure or the shape of the molecule. Okay, the reason we have because each of the water molecule, the structure is kind of like this. Okay, it's a band structure. If we sorry. Those two are invisible. So what you can see is a structure like this. This is the structure of water. So if we're looking at the real structure, and this is generally is a water molecule, right? So this angle is about 104.5. Okay, so that's why if you're looking at the structure of this, generally the angle over here is about. Well, if we talk about the angle of this, it's about these angles. So that's why we can have the flake shape, okay, like that. All right. So we're going to talk about one of the model. Then this model is called VSEPR. Okay, what does that mean? The V means valence. S is a shell, valence shell, and we know what is a shell it is, right? The shell is generally where the electron can orbit around the nucleus. And the EP means electron pair. Valence shell, electron pair, and repulsion. Okay, so another word, the valence shell and the electron pair, they're going to repel to each other in the space. So that is why they have to occupy, each of those parts will occupy their own space. And that is why, because of the repulsion between each of those space, and then we're going to form a structure. So let's just give you one of the example, the video, the demonstration. And this is, we're using balloon as like a lone pair with lone pairs. You can think about nuclear is right in the middle, right? And if you have the electron shell, and the electron shell is really big, just like the balloon, right? And or the lone pairs also, the lone pairs occupy a very big space. It's just like a balloon. So we can use the balloon as those electron pair or the shell, electron shell, valence shell, or the electron pair. And then let's see why those shape we can form. Let's see.
Today we will talk about valence shell electron pair repulsion theory, VSEPR. In today's visualization, you have to think of electron pairs as balloons. So imagine that we have some atom in the center here and we have electron pairs around it. If V-separ tells us that the electron pairs will try to get as far away from each other as possible, and so we can use these balloons to figure out what those shapes would be. So some atoms or molecules have 2 electron pairs around the center atom, and if we tie then 2 balloons together and look what shape those make, we can see that they make a straight line. They're right across from each other, 180-degree bond angle. However, if we take 3 pairs, 3 balloons, and tie them together, you can see that this is the arrangement that we get. I'm not making them into that, that's just kind of the natural lowest energy state that they can go into. So in this, you have, imagine that the atom is at the center, you have these are electron pairs around it, and you have 120-degree bond angles, and it's flat. This structure, that last one is called linear, this structure is called trigonal because it's got 3 sides, but planar because it's flat. Trigonal planar. If we then go ahead and throw a 4th pair on there, not easy to do. There we go. We can see that they take this sort of, it's almost like a tripod arrangement where you have each of the pairs is sort of, if you look at these real closely, these balloons are not flat, they're pointing down a little bit. Down, 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 just a little bit, and this one's going straight up over the top. This is called a tetrahedral. Named so because it has 4 faces, tetra, 4, hedra, face. Faces, I guess. Tetrahedron is the singular. So you have 1 face, you have like a, think of it kind of like a pyramid. I don't want to say that too much because there are other things we call pyramids. This is a tetrahedron, but you have 4 faces. You have a face here, 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 and on the bottom. The bond angle here is, bond angles here are not easy to necessarily visualize, but you can tell that they're more than 90 degrees, but not as much as 120. It turns out that the number is 109.5. And so those are the basic arrangements for electron pairs around the central atom in Chem 1 for 2, 3, and 4 pairs.
Okay, so this is generally is talking about we have 2 those repulsion, and then you're going to see a linear structure, something like that, right? So this is a linear. We have 2 repulsion, which means this is central. The 2 repulsion we generally talk about how much those repulsion that the central atom can have. Okay. Central atom, those guy has a 1 bond over here, then this is one of the repulsion, and this is another, this is like the electron shell, and this is another electron shell. Those 2 electron shells will repel to each other. Then you will have a linear structure like this. But not just the single bond, you see. Double bonds can also making the similar structure. This is a linear, and this is also a linear. That makes sense, right? Yeah. But this one is a carbon dioxide. We have 2 double bonds. And you see 2 double bonds also give you 2 different valence shell, and then they're also going to repel to each other to maintain a linear structure. It makes sense, right? So we will talk about this later. Trigonal planar, I don't have an example, but we do have the tetrahedral up here, right? The tetrahedral, then they're going to have the structure up here. This one is a 3D instead of 2D, right? If we talk about the trigonal planar or the linear shape, those are 2D structure, but this one is a 4D structure. This is 3D structure, not 4D structure. Anyway, and we have 2 more complicated structure, okay? So this is a 3 repulsion among the central atom. But right now here, we have 5 repulsions between among the central atom. You see, the central atom over here, then they are going to have 5 of the repulsion. We have 2 on the top and 3 in the middle. So this structure we give is also another name. This one is called the trigonal bipyramidal. The trigonal bipyramidal. We will talk about why trigonal. If you're looking at it here, this is like a triangle in the middle. So this is a trigonal. And so trigonal bipyramidal, you can think about as a 2 trigonal pyramidal, because bi means 2, right? So that means just a 2 pyramidal, 2 trigonal pyramidal. Trigonal pyramidal. So you see this, the end, the bottom here, this is a triangle over here. And then the top part is one of the trigonal pyramids. And the bottom part actually is another trigonal pyramid. So that's why this is called the trigonal bipyramidal, because they have a 2 pyramid over there. Okay, yeah. And the last one has a 6 repulsion among the central atoms. 6 repulsion. Okay, so this is the most complicated structure that's the nuclear power occur. Okay, so which means the central atom can have a 6 repulsion. This is a maximum. Okay, they cannot have a 7 repulsion. That's impossible. Okay, so 6 is maximum, and this structure we give it a name is called. This is what we call the octahedron. Octa means 8, right? Octahedron means 8 face. Like this guy tetrahedron means 4 faces, and this is 8 face. Then you can see the top part is a pyramid, and this top part, if you see this, is what you can see in the Egypt, the pyramid, right? They have the rectangle in the bottom parts, and then they have a 4 face, right? 1, 2, 3, 4, 4 face. And the bottom part is exactly the same. So they also has a 4 face. So totally that's 8. So that's why this is called the octahedron. Okay, it's called an octahedron. So that's why we're going to discuss. Okay, so generally there's no such reason why you form this. The reason is because the electrons repel to each other. They occupy each of the electron shell or the lone pairs, they occupy the space. They have to, when you have these numbers of those repulsion, the shells of there, they have to repel to each other to form this structure. That's it. Just like the balloon. If you have 4 balloons, you have to making the tetrahedral shape. If you have 3 balloons, then you have to making the trigonal planet. That makes sense, right? Yeah. So that is why. Okay, that is why. So this generally is just what you're gonna remember. That's it. So you're gonna remember it. But before we talk about in detail, I'm going to talk about, okay, so how do you count? How do I count? How do I know how many those spheres, the shells or the lone pairs of them, right? I need to count. I know if we have 2, that's a linear, right? If we have 3, that's a trigonal planar. If we have 4, that's a tetrahedral. You have 5, that's a trigonal bipyramidal. If we have a 6, that's an octahedral. But how can we determine how many numbers of those repulsions that we can have, right? So this is the first part we need to know. And this part is called the electron domain. So as long as if you know the number of the electron domain in general, you will know the general shape of those structure. Okay. So, but what is the electron domain? Okay, electron domain, just like we'll say, okay, if you have if the central atom connect single bonds, each of this count 1 electron domain. That makes sense, right? But the double bonds over here also count 1 of the electron domain. This guy has 2 double bonds, and then they have a 2 electron domain. So that's why they are going to making a linear shape. Okay, so all of those are bonding domain. The electron domain, including 2 things. One is a bonding domain. Binding domain. The other one is called the lone pair. So binding domain, each of the binding domain count one of the domain, electron domain. The single bonds, double bond, and a triple bond. Each of these are count one electron domain. So this guy all count one of the electron domain. Lone pairs also count one electron domain. Okay, so electron domain counted by the bonding domain, single bond, double bond, triple bonds. Lone pairs also counted. So that's why if we talk about, you see this carbon connect with a 4 bond. How many electron domain for this carbon? 4. They have a 4 electron domain, right? Each of the single electron count for the one of the electron domain. So this guy has a 4 electron domain. So that's why the structure of this, if the central ion is a carbon and this guy has a 4 electron domain, the geometry should be like this. Okay, should be like this. It makes sense, right? They have to be like this, tetrahedral shape. Okay, and but if you have this carbon has one double bonds, sorry, they have 1 double bonds and 2 single bonds, then this guy gonna have a 3 electron instead of 4. Right, because we talk about single bond, double bond, and triple bonds are all count 1 electron domain. So this guy gonna have a 3 electron domain. Well, if they have a 3 electron domain, then what is the geometry? This guy will be like this, and this will be a trigonoplanar shape, right? So you see, they're just changing the structure, so they only have the different bonding, then the geometry structure is completely different. This guy is a planar in a flat shape, but this one is a 3D shape. You see? And if you have the carbon, this one has the triple bonds and 1 single bonds over here. Then they only have a 2 electron domain. That make this structure as even just become a linear shape. That makes sense, right? Because they only have a 2 electron domain, so they are become a linear shape. So that's why you see the structure is different based on the different domain they have. Okay. And then we talk about the nitrogen, right? Nitrogen, this nitrogen has a 4 electron domain. Why? Because lone pairs count 1 electron domain. So this guy has a lone pair, and the lone pair count 1 electron domain. They have a 3 bonding domain, 3 single bonds, 3 bonding domain. But they also has 1 electron lone pairs. So this guy, technically, the geometry is a tetrahedral. Although they are going to this is a tetrahedral shape for the electron domain. Okay. But if you're talking about the nitrogen over here, this guy has a lone pair and 1 single bond, 1 triple bond, 1 double bonds. Well, this one will be the same structure like this. This is going to be trigonoplanar. Okay, because they only have 3 electron domain, 1 single bond, 1 double bonds, and 1 lone pair. And these are 3 electron domain, then making a trigonoplanar shape. And if this nitrogen has lone pairs and 1 triple bonds over here, and then, well, we shouldn't write like this. This guy will be a linear shape because they have 2 lone pairs, 2 electron domain over here. That's going to be linear. Are you clear with this? Okay, yeah. So that's why when the geometry for those structure are completely different. But there's a variation between each of the electron domains. So right now, we understand the electron domain, right? Electron domain geometry. But the electron domain geometry not exactly the same like the molecular geometry. The molecule may have their own geometry. Well, I'm talking about it a little bit complicated. Let's just making one of the example over there. For example, we're having two single bonds and one lone pair shows over there. Two single bonds and one lone pair. And just to let you know, this guy, lone pair, is different from the shell. Shell has atom is invisible, but the electron pair is invisible. Like this electrons, right? The electron is very small. Although they occupy very big space, but they're not visible, right? So the real structure, although this guy is a typical planar, right? The typical planar, but since this guy is invisible, then the only seen part is just the bottom parts. The bottom parts is not exactly the planar, it's a bad state. It makes sense, right? So that's why we have a sum of the variation. Or you can see like this. This is tetrahedral, right? If we have only 3 bonds, but the top part is invisible, which is a lone pairs. So when you get rid of this, originally the geometry is a tetrahedral, but since this guy is gone, then they're going to become another shape. It makes sense, right? And this shape we will give it another name. Because this is not exactly an tetrahedral shape, and also not a typical planar shape. So we have to give it another name. But you need to understand that this structure is coming from tetrahedral, right? And then if we have a 2 invisible structure, if we have 2 invisible lone pairs, then it becomes a 2D instead of 3D, right? So this is a band shape. And this is generally the structure for the water body, right? This is the structure for the water body. We have water have 2 lone pairs, but that's invisible. The left over is just that. So that's why this is the bottom one. Yeah. So that's why the next part I'm going to give you a big table, and we're going to draw together for a big table. And then you need to start a new page with the big table. I recommend you to do this in a landscape. The landscape, right? So in this case, you can have enough space to write the big table. I probably don't have enough time to talk about all the table, okay? But I'm going to talk about part of them, and then next time we will keep continuing. Okay. This is a very important part because if you do the organic chemistry, this is very essential. Okay? Very essential. Or okay, so let's draw the table. To be honest, there's no all of those information you have to remember. Yeah, you have to remember because in the final exam, we're not allowed the cheat sheets for this. So you have to remember this. And we will do one of the last lab, which is talking about this. So hopefully it will help you to remember. Yes.
Oh, no. Final exam. Zero pages. Online LinkedIn.
I have some of the practice, yeah, for you. I will give this maybe on Monday, next Monday. Okay, you can do the practice. We will have the exam on Wednesday, right? Yeah, or let me see. Or I can give that to you on Wednesday. Which one? Wednesday. Okay, yeah. Sure, yeah, I can give that to you. And the final take home exam, actually, the take home exam, not final exam, also is a practice for everything. Okay. Yeah. But I think the best one is the study guide that I gave, not the study guide, the practice I gave you. Chapter 1, chapter 3, right? Last time I gave to you. Those are more close to the style for the ACS. Yeah. Okay, so let's start. The first part is called the number of the electron domain. Number of electron domain. And then the second part is the electron domain geometry. Then third column, that's it's called the number of bonding domain. And then number of lone pair. Then is the molecular geometry. And then is a formula. And the example. The last one is called the hybridization. I haven't talked about hybridization yet, but we will talk about it later, but we're gonna write down. Hybridization. Okay, so that's it. Okay, so let's talk about this. So first we start from the smallest. So if the central atom combining with two electron domain, then again, that's gonna be a structure like this, right? It's gonna have a that's gonna be a linear structure. That's gonna be a linear structure for the electron domain geometry. And so this guy has a two bonding domain and no lone pairs. The molecular geometry for this guy also a linear shape. For the former, we usually write is it's called AX2 or AB2, but let's just write AX2. The X means it's the side atoms. They have two side atoms combined together. One of the example is what we write CO2, right? CO2 is one of the example. This is the linear shape for the CO2. Central atom carbon containing two double bonds, and each of this, so each two double bonds, two electron domain, and then they are making a linear shape. Okay. If we talk about hybridization, that's gonna be sp hybridization. Okay, don't worry about what that, just write it down. We will talk about later. Okay, what is the sp? So that's it. This is only for two electron domain. Then let's discuss a three electron domain. So if we have three electron domain, the electron domain geometry is called a trigonal planar. It's called a trigonal planar, trigonal, trigonal planar. So trigonal planar, and this is the electron domain. Then we're going to have a variation. If this trigonal planar, the electron domain has a three bonding domain, there's no lone pairs, which means everything is visible. Then the molecular geometry will be just the trigonal planar. If everything is visible, then that's gonna be just exactly the same, just like the electron domain structure, trigonal planar. And then the former is just AX3, which means one central atom plus three of the side atoms, AX3. So one of the example for this one is SO2. SO2, this is a sulfur dioxide. Sulfur dioxide is a structure like this. If you're looking at the molecule, sulfur dioxide, this is sulfur dioxide. Is this? Is a BF3. Sorry. Sulfur dioxide is another. So BF3, boron trifluoride. Boron trifluoride has a one boron in the middle and a fluoride on the side. So that's why every time when I write a boron trifluoride, I'd like to write a structure like this. And this is the Lewis structure, but also follow the exactly shape of the boron trifluoride. Okay. So the hybridization for the boron is sp2 hybridization. Okay, so here the hybridization we all talk about the central atom. Then we're going to have the variation. So what if we only have two bonding domain and we have a one lone pair? If we have a two bonding domain and one lone pair, then the geometry will not be like that. Okay, so let's see. Just like this. If this guy has a two lone pair, you see, this guy has a two bonding domain, which is we have a two double bonds, one lone pair, which is the lone pair shown here, and the real visible one is just a two two double bonds. The top part is this part is invisible, so the left over instead of the signal planar against it. It is that so this is the invisible part. And you so that's why if we have only two lone pairs, two single bonds, sorry, not two single bonds, two bonding domain. Either is a single bond, double bonds, and then we have a one lone pair shows up here. Totally, you see, this is a two double bonds and one lone pair, so they have a 3 electron domain. And since this guy is invisible, so left over it just bends. So now this guy become a band. So the formula to write like this is with AX2, and then you write E over here. The E means electron pairs, electron lone pair. So AX2E, and that means we still have a 3 electron domain, but they have 2 bonds and 1 electron lone pair. One of the example is SO2. SO2 sulfur containing 2 double bonds and 1 lone pair over here. And if you're looking at here, sulfur actually not follow the octet, but this is the best structure, Lewis structure for sulfur. And again, there's another structure that we can draw like for sulfur dioxide. Although the other structure is follow octet, but this one is the best. Because I say, remember, we talk about oxygen, it's better have 2 bonds, 2 bonds, right? Either 2 single bonds or 1 double bonds. That makes sense, right? Yeah. And this also, if you're looking at here, the real structure for the sulfur dioxide is just like this. Okay, it's just like this. Sorry, I made the mistake. Would you mind to add a small column in the end? Just a small column. And this small column is a bond angle. It's a bond angle. So for the linear structure, the bond angle is 180, right? 180, the bond angle. For the trigonal planar, then that's a 120. That makes sense, right? Because there's a plane that divided by 3, so each of the bond angle is 120. But if you're talking about this is a variation, right? If we have a lone pairs shows up there, then the bond angle not exactly is 120. It's a little bit smaller. Because usually the lone pairs is a much bigger than the shell, the electron shell. So the bigger size of the lone pair is kind of like pushing those bond angle a little bit closer to each other. So make the bond angle is not exactly 120. Instead of they're doing like a little bit less than 120, but not exactly. So that's why the bond angle for the sulfur dioxide is 119 instead of 120, but it's come from the 120. Are you clear? Okay, so this is smaller than 120. Okay, different structure may be different, may vary, but usually is a smaller than 120, but not too far away. If you're talking about hybridization, that's going to be the same, sp2 hybridization. As long as we have the 3 electron domain, then they all have sp2 hybridization. So this is two of the structure electron domain. Let's talk about 4. If we have a 4 electron domain, then that's just like this. 4 electron domain is this one. It's called the tetrahedral. It's called a tetrahedral. So tetrahedral, this is a 4 electron domain. But in this 4 electron domain, if we have a 4 bonding domain, no lone pairs, then generally the molecule will be exactly shaped like the electron domain geometry, electron domain geometry, which is also a tetrahedron. So the formula will be just the AX4 because this guy has a 4 side atoms. Okay. The one of the example is the methane, CH4 is the methane. Okay. So when we write the methane like this, since this is 3D, then we are going to have another way to write a 3D. How can we write a 3D in a 2D in the paper? Okay. So if you're looking at this tetrahedral, and in general, they do have a different way, right? So if you're looking at this top atom, and this atom, and the central atom, those three are in the same plane. That makes sense, right? Doesn't matter how you rotate it, you always can find one and the other one, and this three are in the same plane, right? So they give you the one is sticking out, one is pointing inside. So the sticking outside, we're using a wedge to represent. And the pointing inside, we're using a dash. So this is a way we draw the 3D structure. This is called a wedge and a dash structure. So you have a central atom, carbon over here. Then they put the hydrogen on the top. They are the hydrogen in the same plane. So those three are in the same plane. And then we're drawing wedge and a dash. Wedge is the one pointing out. Dash is the one stick is pointing inside. So wedge, this hydrogen is pointing out. Dash is the hydrogen that's pointing inside. Okay, so this is generally how we draw the three structure. Make sense, right? So wedge and dash. So that's a 3D structure for the tetrahedron. Okay, wedge, we're using wedge and a dash to represent. Wedge means it's pointing out. Dash means pointing inside. Okay, yeah. So this is one of the example. And for the hybridization, we're using sp3 hybridization. The bond angle we talk about, this bond angle is about 109.5. This is a bond angle, the 109.5. So if you're looking at the structure like this, so if we have a structure, then that's going to be the tetrahedral. Show the bond angle. Each of the bond angle are all 109.5. Okay, doesn't matter which bond angle, but they all 109.5. So one of the example is just a methane. So this is a methane. Okay, the carbon inside and the hydrogen outside. Then that's a 109.5 for the bond angle. Are you clear? Okay. Okay, so I'm going to stop here. So next time we're going to continue to talk about all the structures, including the 5 electron domain and the 6 electron domain. Okay, they have some of the variation for the geometry. All right, so I think I'm done for today, and then let's take a break. I will grab the practice for everyone. And I strongly recommend that please don't leave. Okay, I know you can work on this at home, but it's more efficient if you work in the classroom. Okay.